So we're going to cover two main equations today that we typically find in rocket propulsion. And we're going to learn how to derive these equations and how to use them to answer two example problems. So the first equation is all about how we can determine the change in velocity of a rocket. So change in velocity, which is equal to the final velocity of the rocket minus the rocket's initial velocity, and that's equal to the velocity of the exhaust multiplied by the natural logarithm of the initial mass of the rocket, capital M sub I, divided by the final mass of the rocket. So what do I mean by this? So the initial mass of the rocket is whatever the mass of the rocket is when we have a certain amount of fuel in the rocket. So it could be completely filled with fuel, or it could be half filled with fuel. But the final mass of the rocket, so that's the initial mass of the rocket, the final mass of the rocket is the rocket when it's expelled or ejected some of the fuel. So let's say the fuel was about 50% here, and let's say after some time, about 25% of the fuel is remaining, and that would be the final mass of the rocket. And the exhaust velocity is the speed at which the particles of gas are ejected out of the rocket. So for example, the Saturn V rocket would have an exhaust velocity of something like 3,000 meters per second. So we're going to learn how to use this equation. We're going to learn how to derive it, but there's also another equation that we're going to look at, which is calculating the thrust or the force that the rocket experiences when it's ejecting material out the other end. So the thrust is equal to the mass of the rocket multiplied by the rate of change of velocity with time, or the acceleration. So that's force is equal to mass times acceleration. That's Newton's second law. But that's also equal to the absolute value of the exhaust velocity multiplied by the burn rate of the rocket. So the change in the mass of the rocket divided by a small change in time. And we've got the absolute value here, which means that this value is always going to be positive. We're always going to have a positive force in the positive y direction. So we're going to learn how to derive that and use that as well. So let's imagine we have a reference frame here where the Earth is at the origin of this reference frame. And within this reference frame, we have a rocket moving at a certain velocity in the x direction. And the mass of the rocket, or the total mass of the rocket, is the mass of the rocket plus a small amount of fuel that we're going to eject out the back. And this is before. And the initial momentum of this rocket is equal to the mass, total mass, multiplied by its current velocity. Now, after some time t, delta t, we've burnt some fuel, or we've ejected some fuel out the back, which has a mass of our delta m here, and the remaining rocket has a mass of capital M. But the speed of the rocket now is equal to the initial velocity plus some extra velocity here. And the velocity of the exhaust is equal to V sub E. And this value here is in reference to the rocket itself. So if you were sitting on the rocket here and you were observing this fuel rushing out the back and you measured its speed, this is the value you'll get. So the final momentum of this rocket is equal to the mass of the rocket multiplied by the rocket's new velocity, so velocity plus delta V, and this is the momentum of the rocket. But we also need to include the momentum of the exhaust gases. So delta M is the mass of the exhaust coming out the back, multiplied by the velocity of that exhaust as seen from the Earth's reference frame. So that's the velocity, the initial velocity of the rocket, minus the velocity of the exhaust. So that's the momentum of exhaust. So let's imagine the rocket is moving at, say, 5 kilometers per second. So V is equal to 5 kilometers per second. But the exhaust gases, VE, only move at, say, 2 kilometers per second. So if you were sitting on the rocket, you'd see these exhaust gases moving in the negative X direction at 2 kilometers per second. But if you're in the Earth's reference frame, so if you're sitting on the Earth and looking at this rocket moving away from you at 5 kilometers per second, the exhaust coming out of the rocket would also be moving away from you at 5 kilometers per second minus 2 kilometers per second, which will equal 3 kilometers per second in the positive X direction. So this is what this expression means here. It's the momentum of the exhaust gases in the Earth's reference frame. Now, the law of conservation of linear momentum states that the total momentum of all particles within a closed system remains constant. So effectively, what we're saying with our rocket here is that all the momentum of the fuel and the rocket before the rocket fires should be equal to the total momentum of the fuel and the rocket itself after it's fired its engines. So the initial momentum in this closed system should be equal to the final momentum, which means we can tie these two expressions together. So the initial momentum, which is the mass of the rocket plus a little bit of fuel that's ejected out of the back, multiplied by the rocket's initial velocity, will be equal to the total mass of the rocket plus its new speed plus the momentum of the exhaust. And we can expand this out now and simplify it. So mass times velocity plus the mass of the fuel times velocity is equal to capital M multiplied by velocity plus capital M delta V plus the small mass of the fuel multiplied by velocity minus delta M, the velocity of the exhaust. And you see here on both sides of the equal sign, there are terms that we can cancel out. So this term here can cancel, this term can cancel, and we're left with these two terms here. So we've got the mass of the rocket, delta V, is equal to the mass of the fuel and the speed of the exhaust. And the linear momentum is conserved within this closed system. So what happens now if we take the limit of delta t and make this approach 0, then delta v will approach dv, and the small amount of fuel being ejected becomes dm. So our previous expression becomes the mass of the rocket, delta v, is equal to the velocity of the exhaust, delta m, where delta m is the change in the mass of the fuel being ejected, which is also equal to negative the change in mass of the rocket. because the rocket is losing a small amount of mass when the amount of mass of the exhaust is increasing. So we can also write this expression like this. Capital M dV is equal to negative velocity of the exhaust multiplied by the change in mass of the rocket, the infinitesimal change in the mass of the rocket. We can divide both sides of the equation by the mass, total mass of the rocket, and then we can integrate both sides. So this side represents the change in speed of the rocket, so the initial velocity and the final velocity. And this side, we're looking at the change in the mass of the rocket itself from its initial mass and its final mass. And we can remove this velocity term outside of the brackets. So we got negative velocity of the exhaust is the definite integral between the initial mass and the final mass of the rocket, the total mass of the rocket to the power of -1 multiplied by the infinitesimal change in mass of the rocket. Now, what we have to do here, we can't use the power rule for integration, and the power rule is written like this. So x to the power of n dx, the integral of that is equal to x n plus 1 divided by n plus 1 plus c. So this cannot work when n is equal to -1. We can't use it. So in situations like this where we've got a value to the power of -1, when we integrate, this becomes the natural log of this value here. So we get negative velocity of the exhaust, natural logarithm of the mass of the rocket between the initial mass and the final mass. Now, there is a way to prove this result here, which you'll learn in introductory calculus, but I'm not going to go through this in this video. But if you're interested, then let me know in the comments below. So let's expand this out. So we've got negative velocity of the exhaust multiplied by the logarithm of the final mass minus the logarithm, natural logarithm of the initial mass. If we multiply through by -1, so multiply through by -1, this becomes positive, that becomes negative, and that becomes positive. And we can write this out as the velocity of the exhaust is equal to the natural logarithm of the initial mass minus the natural logarithm of the final mass. And using the quotient rule from the law, which is one of the laws of logarithms, where a logarithm, say of base a, of x over y is equal to the logarithm base a of x minus the logarithm base a of y. So we can simplify this expression here into a fraction. So we get velocity of the exhaust, natural logarithm of the initial mass of the rocket divided by the final mass of the rocket. And this is equal to the change in the velocity of the rocket itself. And this is the expression for the rocket propulsion. In order to get the thrust of our rocket, we need to use this expression. And we got this expression because linear momentum is conserved within a closed system. So the initial momentum of our rocket is equal to the final momentum. And we've just simplified this expression. So we saw before that the mass of the rocket, delta V, is equal to the velocity of the exhaust multiplied by an infinitesimal change in mass of the exhaust gases, but this is equal to negative the velocity of the exhaust multiplied by a small change in mass of the rocket itself. Now, this is because the small change in mass of the exhaust gases is equal to the negative change in mass of the rocket. So when you're getting rid of fuel from the rocket loses the equivalent amount of mass. So we can use Newton's second law, force is equal to mass times acceleration, to obtain the thrust of this rocket when it's ejecting fuel at a velocity of v sub e. So the thrust, which is simply the force exerted on the rocket by the ejected exhaust gases, is equal to the mass of the rocket itself multiplied by dv over dt, which is the acceleration. And what we're doing here is we're dividing both sides of the equation by delta t, and we've got the absolute value of the exhaust multiplied by the change in the mass of the rocket, delta t, and this is the burn rate. So it's the rate of change of the mass of the rocket. So if we wanted to increase the thrust of our rocket, we can do two things. We can increase the exhaust velocity, so we can use a different kind of exhaust mixture, or we can use charged particles, for example, and they typically have a high velocity. But the problem with that is that this burn rate would be very low for an ion engine. The second thing we can do is increase the burn rate, so we can improve the efficiency of our rocket engine, so it can expel more mass out the back of it per unit time. So let's try some practice problems here. Imagine we've got the first stage of a Saturn V rocket. So that's the first stage there. And it consumes fuel and oxidizer at the rate of 1.50 times 10 to the 4 kilograms per second. So this is the burn rate, delta M over delta T. So it's burning 15 tons of fuel per second. Now the exhaust speed of this fuel coming out the back, V sub E, is equal to 2.60 times 10 to the 3 meters per second. How can we calculate the thrust produced by these engines? So the equation for thrust is equal to the absolute value of the velocity of the exhaust multiplied by the burn rate, so the rate of change of mass of the rocket. So 2.60 times 10 to the 3 meters per second multiplied by the burn rate, which is 15 tons per second, 1.50 times 10 to the 4 kilograms per second. This gives us units of meters per kilogram per second squared, which is the units for newtons. So meters, kilograms per second squared, that's Newton. And this gives us a value of 3.90 times 10 to the 7 newtons of thrust. So with this information, how can we work out the acceleration of this Saturn V rocket as it's leaving the launch pad? So if the upward direction is positive y, how can we find the acceleration in the positive y direction? And the mass of the Saturn V rocket is equal to 3.0 times 10 to the 6 kilograms, so 3,000 tons. So the thrust from the rocket is in the positive y direction. So this is the thrust. And this particle here represents our rocket. But we also need to consider the mass of the rocket multiplied by the gravitational acceleration, which is the force of gravity on the rocket. So we need to find the sum of all the forces acting on the rocket in the y direction, which is equal to the thrust minus the mass of the rocket times gravitational acceleration. And this is equal to the mass of the rocket times the acceleration in the positive y direction. And again, this is Newton's second law. So This represents the total mass acting on the rocket, which is equal to the rocket's mass multiplied by the acceleration on the rocket. So we can simply plug in these values. So the thrust is 39 million newtons, 3.90 times 10 to the 7 newtons, minus the mass of the rocket, 3,000 tons, 3.00 times 10 to the 6 kilograms, multiplied by the acceleration due to gravity, 9.81 meters per second squared. And this is equal to the mass of the rocket again, multiplied by its upward acceleration due to the exhaust gases coming out. So the acceleration, after summing this all together, is equal to 3.19 meters per second squared. So we try one more question. We've got a model rocket here, and the thrust of this model rocket, or the engine of this model rocket, normally the engine's about this size, they're quite small. So the thrust produced by this engine, on average, is equal to 5.26 newtons. The rocket motor has a mass of 0.0255 kilograms. The total amount of fuel contained in this rocket is equal to 0.0127 kilograms, and the rocket body has a mass of 0.0535 kilograms. So if the duration of the burn of this rocket motor is equal to 1.90 seconds, what's the average exhaust speed of the gases coming out of this rocket motor? So we can use this equation. The thrust is equal to the absolute value of the exhaust speeds multiplied by the burn rate of this rocket. We've already been given the thrust at 5.26 newtons, so put 5.26 newtons here. And we're trying to work out the velocity of the exhaust, but we're not directly given the burn rate. But we've got the mass of the fuel here, and we've got the time it takes to burn this mass of fuel. So all we need to do is put the mass of the fuel, 0.0127 kilograms here on the top, and divide it by the total amount of time we've got here, so 1.90 seconds, and that's our burn rate. When we multiply through, we get an exhaust velocity of 787 meters per second for the exhaust gases shooting out the back. So we got the exhaust velocity, but what would the final velocity of the rocket be? Say if this rocket is in empty space, far away from the Earth, and we want to find out how fast this rocket can go with its mass given this exhaust velocity. So we need to use this equation first of all, so the final velocity of the rocket minus the initial velocity of the rocket, and the initial velocity here we're going to assume to be at 0 meters per second, is equal to the exhaust velocity multiplied by the natural logarithm of the initial mass of the rocket plus the fuel divided by the final mass of the rocket. We need to work out what the initial and final masses are going to be. We've got all this information here to work it out. So because the initial velocity is 0, we can remove that from this equation here. We've got the final velocity is equal to 787 meters per second. And we've got the natural logarithm of the initial mass. So the initial mass is going to be the mass of the rocket motor. And this is the total mass of the rocket motor itself plus the fuel. so 0.0255 kilograms, plus the mass of the rocket body itself, so 0.0535 kilograms. And the final mass is going to be the mass of the rocket body, the mass of the rocket motor, but minus the mass of the fuel, because the fuel doesn't belong to the rocket anymore. It's been expelled out the back. So that'd be 0.0255 kilograms plus 0.0535 kilograms minus 0.0127 kilograms. And when we sum this all together, we get a final velocity for our rocket being 138 meters per second to 3 significant figures.